vai apresentar trabalho sobre recuperação de, eu não sei como é que você pode dizer,
gás de xisto,
através de injeção de oxigênio e combustão.
Thank you very much. So I would like to thank for the invitation. It's always a pleasure to be at IMPA. I started some time ago as a postdoc in TU Delft, and here I will present some ongoing work, so it's not finished yet, but I hope I will present a lot of motivation, well, with Professor Browning, and I hope I will stay a lot of motivation part, and then I show some difficulties which appear with simulation of this type of production. Some models we are trying to study, and what's going next. Well, first of all, what's shale gas? As Professor Browning says earlier, there are all these worries about the production of oil, production of gas, and they are vanishing. So the people are really interested in looking for new sources of hydrocarbons. And well, one of them is a shale gas. So I take some nice slides from I borrow them from a lot of other people presentations and papers. I will show them first. So this is a picture with biggest reserves of shale gas in the world. Now the only country that produces shale gas in a high scale is US, but the biggest reserves are in China. Brazil also is beyond 10 countries with the biggest reserves. So, well, here is US graphic. Now it corresponds to barely 23% of total gas produced, but the expectation is in 2035 to be almost half of all gas produced to be shale gas. Well, this is a nice picture that shows that the conventional gas, which is mostly produced now, is not so big volumes in total volumes in the world. So the shale gas, we have more shale gas possible to recover than, in fact, conventional gas. But the problem is that jointly with this good news, we have decreasing permeability. So the shale gas, the permeabilities are close to nanodarcies, which I will explain a little bit further. We have decreased reservoir quality, so not only permeability, but porosity too is becoming worse. And of course, it needs much more investigation and technology. So this is a good part, because this means that we will have work for decades. Well, this is a comparison from three more produced types of gas. So the principal thing is that shale gas has a scale of nanodarcy permeability, or the shales where the gas is, the porous media where the gas is much less. The diffusion is very complicated. The conduction, diffusion so the displacement of this gas is difficult. The tight gas is millidarcies, and conventional gas is darcy scale. Also, the porosity is smaller, so the total amount of gas in cubic meter of porous media is much smaller for shale gas. Well, how the shale gas is produced and why it starts to be produced now? Because of two technologies. One of them is, the principle is a horizontal, horizontal wells, which you can put very close to the formation, so the gas doesn't have to be transported to long distances. It only has to be transported to small distances. And another technology that possible this production is hydraulic fracturing, which is you pump like a bomb, amount of water. You produce some waves. These waves make cracks in a formation, and for this crack, the gas escapes from the formation to your well. So this is the way you produce this type of gas. Well, however, it comes this type of technology comes with a lot of problems, which are resumed here. Principally, you have some folds that are you already have them in your formation. So this hydraulic fracturing can make them bigger, and the water and contaminated water, because you not only pump water but some chemicals to help you in fracturing. These things can go into aquifers. Also, the gas can go out upside and mix with water. So you have methane in some places in the United States. You have methane from the drinking water, and there is very nice videos that I didn't found to put here. That one of these guys put a fire on the water that his cows was drinking, and all the water takes fire immediately, which is really impressive. Yeah, but I think he didn't put his cows to drink vodka. Maybe milk will be much better, yeah, in this sense. But okay, so we have these environmental impacts: contamination of groundwater, depletion of fresh. You need a lot of fresh water, of course, to pump here. So you will spend some fresh water for this. So the gas can escape and chemicals can escape to the surface and to aquifers, air quality because of the methane that are escaping and so on. So like we work some years with combustion, and why not using combustion, in situ combustion, to try to think if in situ combustion can improve this production. So, well, this motivates the work. So basically, the hugest difficulty is this one. So the scale of the permeability scale is this, and there are a lot of effects. Well, so the first question, well, why combustion? Because combustion you only pump air inside, so you don't have fresh water, and you don't have these chemicals that you will pump. You will only pump air. Then you will make a combustion, but maybe combustion, of course, will somehow change this environment, but maybe not so much as hydraulic fracturing. So this effect will be less. So here, of course, I hide another things, etc., which I don't want to speak because combustion will definitely not solve them. But contamination of groundwater, depletion of fresh water, and migration of gas and chemicals to surface, combustion is a better way maybe to avoid. Okay. So the principal problem we found is to model the permeability as function of temperature. Because when you study permeability function of temperature for this type of, this range of permeabilities, of nanodarcies to microdarcies, it appears a lot of effects which are not already modeled. There is no solid theory about them, and at least not solid mathematical theory with, that we can put in mathematical model. So this is so searching this is not trivial. Well, and we will use two approximations. The first one uses Klinkenberg factor, which says that the permeability. Well, I based on these two works, but there are dozens, tens of them. So the permeability is based on some reference permeability, and these two factors multiplying them, where alpha is some very obscure parameter which is found from experiments, and Kn is the Knudsen diffusion given by this formula depending on temperature. So, well, here are more or less explanation how you obtain this alpha and another parameters. Well, this one are almost okay. Alpha is obtained experimentally from this formula, and well, these numbers I take from the works of Sivan, but other works use this formula and experimentally obtain different type of parameters. Because of course here you have this formula and they match some experimental points with the formula and obtain different matches. Okay, so this this approach gives the function like this. So temperature and permeability. This this function doesn't improve a lot permeability with temperature. So another work is Jamaluddin, and they state that, well, I don't have a name for it. They state that if you increase temperature of shale, you will make another effects based on vaporization of blocked water. So there is some trapped water in shale formation. If you put heat on it, this water will escape, and you will have some chemical reaction. So you will have dehydratation, destruction of the lattice, and creation of some microfractures. And this can really increase permeability. So in this work, they state that the better thing you can improve is something like 7 times for this temperature. Well, this is absolute temperature. So what I put in the model, that the good part of this type of approach is that once you improve permeability, it will not come back. So the formation is deformed, and the permeability will be improved forever. So, for example, if you produce a combustion wave that goes through your reservoir, it means that it will improve the permeability of all this part. And later, you can use all this reservoir to produce gas. So it's the function I use in this presentation. You have maximum time. So once it increases, it doesn't come back. And it increases factor of 5 if the temperature goes to 350. Exponential is just based on, it's a shot, so why not exponential? Well, so the function of permeability is like this in temperature, and in time, if once it reaches this value, it will stay for this value forever. Okay, now the first idea was to make the following. If we have this matrix, which is full of methane, and it's very small, the permeability is really small. So we make a horizontal well, we inject air, and we make a combustion wave here inside. This combustion wave will generate heat. Heat will increase the permeability of the nearby formation, and we want to see if this nearby formation increases the production. Well, I have a lot of the model I will show is very simple, so we consider all these assumptions. Some of them are really strong. Basically, we consider the thermal conduction. It will be independent. This is so-called Lavash concept, which means that thermal conductivity in the horizontal direction and the vertical direction, so the perpendicular direction to the well, are independent one from each other. There are a number of works that states why this can be true and why this makes sense from the physical point of view. So we have this transport equation. We have we neglect diffusion diffusion term. We have the thermal losses to the perpendicular direction, and we model the combustion wave here just by some delta function or the approximated delta function. I will show how this is modeled. And in perpendicular direction, we use just heat equation. Well, dimensionalization follows this work, and in a dimensionless form, we have this PDE. So this is horizontal direction. These are the directions perpendicular to the well direction. And we consider radial symmetry, so in 3D, but with radial symmetry. So the Laplacian will have this form. And and then we need a pressure, because the final interest is to measure the production increment. So for pressure equations, we use this diffusion equation for pressure evaluation, and one of the assumptions is that temperature profile independent from pressure. So we can first run temperature profile, and then we obtain the pressure. Of course, pressure will depend on temperature because our permeability function depends on temperature. Well, in dimensionless equation, it stays like this. The numbers ER and EX are different only because of the dimensionalization in R direction and Z direction we take differently to match better the numerical simulations. Okay, these are the initial condition and boundary condition. Basically, we consider that there is inside the hole we have some constant pressure, and the reservoir starts with some reservoir pressure, and there is no flow conditions on the outside boundaries. Well, in order to solve it, we apply Laplace transform. So we take the equation, apply Laplace transform. It becomes Bessel equation. Bessel equation can be solved from Bessel functions of first and second kinds, modified Bessel functions. We make some hypotheses and come to the solution in this form. So now solving the equation, the heat equation perpendicular to whole direction, we substitute, we obtain. So this is a solution along the hole. This is a solution. This is our thermal losses. Substituting an equation, we come to this, and finally, I will not show all the calculations. We take a lot of time and space. So we come to this function, where this is a Laplacian transform of our combustion wave. Combustion wave can be generated just by delta function or by approximated delta function. Here I make them both. So if we approximate it by delta function, the Laplacian transform is 1, so we have an answer. And now we have to calculate. So until this point, all the calculations are analytical, but unfortunately, I cannot calculate the inverse Laplace transform of this stuff. So I use the algorithm proposed in this paper, and we have these results. Here are, if we neglect thermal losses, we just have two standard waves. Here we have a combustion wave. Here we have a thermal wave. Because combustion wave is much faster, so actually this wave is moving. But for numbers we take in this work, so the thermal wave is slow, so you cannot almost see the difference from here to here. And combustion wave is fast, you can see. And here is with thermal losses, so you see that the thermal wave disappears because it smoothly goes, the temperature goes to the reservoir temperature, but combustion wave stays here. Well, it's also possible to make the same calculations with approximated delta function, and using so the equation become a little bit harder with complex error function in the middle, which has to be approximated numerically too. But well, the results are the same. So I first make this one, and then realize that delta function was easy and the result was the same. But okay, well, so we can simulate now the temperature profile and what the effect the temperature makes on permeability. So this is initial. We start with time 2 because for calculate the Laplace transform in time 0, it's singular point, so the integral doesn't converge. So I have to start with some positive time. I start with 2, for example, here. So we have temperature profile. This is the hole. So this line, dark line, I don't know if you can see it easily. This is our well. And here is the formation. So when time advanced, you see that the temperature wave goes in front, and the permeability rises, but only in some small vicinity of the well. So this function of permeability obtained here, I interpolate and use in a simulation for pressure equation. And actually, so with the eye is difficult to see, but here the numbers are a little bit higher than here. So here is the reference one where you have no temperature. So we just run the simulation without temperature increasing, without permeability changes, and here with permeability changes. And using permeability calculated by Klingenbein factor, we obtain 1.72% increment in production. And for this cooking theory, almost 10%. And unfortunately, this was with the speed of wave was changed a little bit to put it in resonance regime, which Alexei told half an hour before. And this means that this approach is not from engineering point of view, is not interesting. Well, unfortunately, because for better situation, we obtain 10%, and this is very particular reservoir because it has 50 centimeters height and 50 centimeters wide. So 50 centimeters is not real size. But in fact, what happens is that we don't generate enough heat inside the hole with combusting methane, and this heat only increases the temperature from the small vicinity of the well, which makes physically, it just makes that you increase your well radius by twice. But this doesn't help with, really helps with production. So for simulation with this size of reservoir of hundreds of meters, which or tens of meters, and the z of kilometer, which is reasonable, the effect is almost nothing. So another approach can be producing the combustion wave inside the formation. So you inject oxygen and produce combustion wave exactly in the same manner was the talk of Alexei. The model is very similar, so I will not stay a long time here. We have almost the same hypothesis, only that there is no liquid phase here because there is no liquid. We are in gas shales. So I make an dimensionalization. We consider this, so we have these dimensionless physical parameters. And for calculating it, I use the Lavash method, which inspired in this work. Of course, we have a lot of other literature which explain it. So I separate the reaction in two layers, the reaction layer, pre-reaction layer. We assume that here the combustion happens and here only conduction happens. With combustion is almost no change in temperature. So it can be easily solved. In reaction layers, the governing equations are these. If you consider a traveling wave, so this psi corresponds to x minus vt. The same thing, so we obtain these equations, and the point of this Zeldovich technique is obtain information about this point, the gluing point of two regions, where we, from this matching, we obtain the speed of the combustion wave, we obtain the combustion wave temperature, and so on. So here are the information about this point, C point. Next, I make same calculations for pre-reaction layer, only for we ignore the generation of heat in a thermal equation, and we approximate the combustion for oxygen and methane. So, well, here are the same information for. So, see, in this layer we can calculate analytically the solution for theta, z, and the gluing point. If we put the two regions together, we obtain the formula for speed from the combustion speed, for the temperature of the combustion temperature, so the highest temperature achieved during combustion. And we dividing one OD by another, we obtain this OD, which will give the third. So we have V is unknown, theta B is unknown, and ZC is unknown. So I need one more equation. This equation will come in this form. So it's it's an OD which will join two points which we know. We can solve it analytically using special exponential special function, special integral function, and obtain this implicit result. Well, I will not show here the numericals because it's not completely ready. But this equation gives for me this theta b, that I obtain the combustion temperature, which matches exactly the numerical simulation, rough numerical simulation, because I don't have them very detailedly. Well, the next work is to try something else, because this approach has some problems, because this theta b is very nice and it's matching numerically, but we see that it also doesn't generate enough heat to increase the temperature for really improve permeability. So we need something else. Something else is to study this stock combustion, because in a shale, in gas shales, there is some other hydrocarbonates which are not gas, methane, which in some possibilities also can be combusted. This is the next topic of research. And to enjoy the excellent laboratories that Dietz laboratories that there is in Delft University, I will try to make some experiment to see if really gas shales can be improved the permeability by heating it. So this is already begun, but it's too early to show something. Well, thank you very much.